that we know a little bit more about the history of the periodic table, I think it's important that we start to study the patterns that we can find on the periodic table. And for this section, I really just want to focus in on the numbers that we find on the periodic table. Now, before we go headlong into this, I think we might want to just talk about the subatomic particles that make up every single atom. Now, you know and love them as the proton, the neutron, and the electron. And you probably also recall where each of these is located. The proton and the neutron are both found on the inside of the nucleus, whereas the electron is left spinning around the outside of the nucleus in what we call the electron cloud. I'm hoping that you also recall the charges of these different particles. The only neutral particle that we have is the aptly named neutron. The proton has a charge of +1, and the electron, kind of its counterpart charge-wise, has a charge of -1. Now let's take a look at this mass business. Now, the proton and the neutron are both about equally matched. The neutron actually weighs a little bit more than a proton, but it doesn't show up here on this screen. We say that they both have the mass of 1 AMU, whereas the electron has a mass of 0 AMU. Now, that's not to say that the electron doesn't have any mass. What this does say actually is that the electron has so little mass that according to everybody's favorite, significant figures, it just is not statistically significant enough to even record anything other than a 0. Now you might be wondering to yourself, what is this thing called an AMU? AMU stands short for atomic mass unit, and it's a relativistic style of unit that we use specifically with these subatomic particles. Now, roughly 1 AMU is approximately the mass of 1 proton. So really by saying 1, we're saying it has the mass of about 1 proton. So the neutron is approximately the same size as a proton, and again, according to significant figures, the electron does not have a statistically significant mass to even record. So take a look at all of these different numbers that we can find on the periodic table. It's actually a little dizzying to see all of these numbers all at once. So rather than focusing on all of them, let's just focus on one element. Let's take a look at my favorite element, carbon. Now this is just a single tile from the whole periodic table, and there's a lot of information that's contained in this tile. Most notably, you'll find the element symbol. This is a shorthand way of representing which element that we're talking about. For most elements, it's either the first 1 or 2 letters of the element name. But for a few of the elements, you're going to find a mismatch between the symbol and the name. And that has to do with when these elements were first discovered and used and talked about. Most of those names go back to either a Latin or a Greek root. For example, sodium has the symbol of Na. Well, that's the symbol is not based off of the modern name sodium, but the ancient name natrium. The same thing can be said of something like gold. Au is the symbol for gold, and that's clearly not the name, the modern name now we know of gold. It's based off of its Latin root, aurum. There are several examples on here. You'll probably want to spend some time familiarizing yourself with them. Another important piece of information on a tile on the periodic table is something called the atomic number. Now this represents the number of protons inside of this individual element. Now it's important to note that the proton here is the most important subatomic particle on this whole periodic table. The number of protons is what determines which element that you're dealing with. It's only the number of protons that determines this. It determines all of the element properties and everything that you really need to know about that particular element. That's a really important number. Now, what's cool about this number is that for neutral atoms, and they're not going to remain neutral for very long, it also represents the number of electrons that we can find. So carbon would have 6 protons and also 6 electrons. Now, what about this number down at the bottom? This is called an average atomic mass, and we'll talk about that again a little bit later in this video. Roughly right now, you can assume that this equals the number of protons plus the number of neutrons. So a quick and dirty way of trying to figure out the number of neutrons on the inside of an element would be to take the two numbers that are found on this tile and simply subtract them. In this case, I would have about 12 minus 6. That would give me the answer of approximately 6 neutrons in this element of carbon. Now, you may be wondering to yourself, well, it's nice that we have all of this information, but why is that number on the bottom a decimal? Like, doesn't carbon have 6 protons and then 6 neutrons? What's the deal with the decimal? I don't get it. Well, it's because not all of the atoms inside of this element actually have the same mass. Some are a little bit skinnier, and some have a little bit more meat on their bones. What we're talking about here is something called an isotope. Isotopes are atoms inside of an element that have the same number of protons. Now that makes them belong to the same element. However, they will have a different number of neutrons. Now, it doesn't affect their identity. They'll still be the same type of atom because of that same number of protons. But like I said, some of them weigh a little bit less, some of them weigh a little bit more. We can represent isotopes by using something called an isotopic symbol. It's a shorthand way of conveying this very important information. Now this time the number that's on the bottom is the atomic number. And again, that is representative of the number of protons on the inside of this element. The top number is now called the mass number. That's a different name than what we used before. It does definitely represent the number of protons plus the number of neutrons. Just like before, if you want to find out the number of neutrons in this isotope, just take these two numbers and subtract them, and you'll easily find the number of neutrons in this particular isotope. In this case, 12 minus 6 would give you 6 neutrons. It's also important to note that this isotopic symbol represents only one atom at a time. Just one atom. So in this particular atom, if we were building it, we could use the isotopic symbol, and I would know that I would need to grab 6 protons and 6 neutrons, and that I would build a carbon nucleus. So this still doesn't quite explain yet why the number that's on the periodic table, though, is a decimal. That's still confusing me. So let's dig into this a little deeper. Well, the number that's on the periodic table, again, is called an average atomic mass, and the most important word in there is average. What we're averaging is all of the mass numbers of every single individual isotope inside of that element. And we say that this is also done according to their abundance. Like you might have a lot more of one type of isotope than another, so you can't just add the numbers up and divide by 2. I'll explain as we continue forward. I think it might be time for an example problem. Now, again, before we move on, it's important to represent that the number on the periodic table represents more than just one atom at a time. This is an average of all of the different atoms that can be found inside of a much larger sample. So here's a sample problem. What is the average atomic mass with an element that has 4 atoms that have a mass number of 4 and 1 atom that has a mass number of 5? So 4 of the atoms have a mass of 4 and 1 of the atoms has a mass of 5, and I need to come up with an average atomic mass. Well, you may have been taught that the most important thing to do when you're coming up with an average is to add together all of the numbers. So I have 4 atoms that have a mass of 4, 1 atom that has a mass of 5. All together, that gets me a total mass of 21. Now to complete that average, I need to divide that number by the 5 total atoms, and that gets me an average atomic mass of 4.2. Once again, I'd like to point out that the numbers given in the problem are mass numbers. These are the masses of the individual isotopes. These are whole numbers and are only found on the isotopic symbol, whereas the number all the way over on the solution side is called the average atomic mass and represents the average of many atoms altogether. That's where you're going to be able to get this lovely little decimal. Now, another important point that we should probably make. In this problem, we said that 4 out of the 5 total atoms all have that same mass. Well, we can actually convert that 4 out of 5 into something more user-friendly, a percentage. 80% of the atoms here have a mass of 4. We call this percentage a percent abundance, and that percent abundance is very important as we move forward. This is how scientists convey this type of information. Let's get you an example so you can see how this problem is going to kind of morph. What is the average atomic mass of an element with 75% of the atoms having a mass of 10 and 25% of the atoms having a mass of 15? Well, we're going to need a new formula now. So the formula for calculating average atomic mass is the mass of the element times its percentage, all added up together. Let's plug and chug our information into this formula. So I know that 75% of the atoms have a mass of 10. So I'm going to take 10 times the decimal form of the percentage, 0.75. And then I'm going to add that to my next isotope, which has a mass of 15 and 25%. So I'm going to multiply that times 0.25. I would repeat this process for however many isotopes I have on the inside of my sample. Luckily here I only have 2. So now I can go ahead and plug and chug in my answer, and I find that the average atomic mass for this problem is 11.25. Now, before we completely exit this topic, I think it's important to note that there is another form of notation when you're dealing with isotopes called hyphen notation. Carbon 12. This is specifically talking about carbon whose mass number, that's that number at the top of the symbol, is 12. And we would refer to this more as something that we would use in a sentence or in writing. And I think you should probably have an example of that as well. This is the most complex example that I'm going to give you here. What is the average atomic mass of boron if it has 2 isotopes? Boron 10 with a percent abundance of 19.8 and boron 11 with a percent abundance of 80.2. Again, let's go back to our formula for average atomic mass. It's the mass of the isotope times its percent abundance in the form of a decimal. Add all of those numbers up for however many isotopes you have in the problem. Luckily here we only have 2. I'm going to plug and chug my numbers in. My first isotope has a mass of 10 and it was 19.8% abundant. In a decimal form, that's 0.198. My second isotope has a mass of 11. Its percent abundance was 80.2. As a decimal, that's 0.802. Time to plug and chug in the calculator, and you can find the final average atomic mass is 10.8.